Welcome to this explainer on Module 1, Solar Fundamentals and Site Assessment. Whether you are literally stepping onto a roof for the very first time, or you're a seasoned installer just looking to sharpen that engineering mindset, this is for you. We're going to build the absolute bedrock, both scientific and practical, that you need for flawless solar installations. Because look, in this industry, long-term success is definitely not just about turning a wrench. It's about deeply, intimately understanding the environment you're actually building in. Let's get to it. To really grasp why we need to master the basics, you have to consider the true cost of getting it wrong. Think about a single shadow from a totally harmless-looking chimney. That tiny shadow can disproportionately tank the power output of an entire string of panels. It's not just a one-to-one loss, right? Even a tiny bit of shade can completely cripple massive production. And that is exactly why this foundational turning isn't just optional, it's absolutely critical if you are going to deliver the energy yields you promise your clients.
So, here's our game plan for today. First, we'll hit the science of solar fundamentals. Second, we'll dive into load analysis and sizing. And finally, we'll cover the physical site survey.
All right, let's jump straight into Section 1, the science of solar fundamentals. It all kicks off with the photovoltaic or PV effect. Simply put, this is the magic that happens inside semiconductor materials, usually silicon. When these materials are exposed to photons from sunlight, they generate voltage and current. By understanding this PV effect, we're establishing how these microscopic atomic-level mechanisms are the absolute bedrock of the massive electrical circuits you'll be managing out in the field. Because think about it, if you don't know how the energy is born, you really can't manage it safely when it scales up to thousands of watts. When the sunlight actually hits the panel, deep inside those cells, there's a junction between N-type and P-type silicon. That specific junction is what facilitates the flow of electrons to create direct current or DC electricity. This is the raw, unrefined power of your system. And you gotta remember, it behaves very differently than the standard alternating current or AC that's flowing through the wall outlets in a house. Now, to turn that invisible science into actionable, real-world numbers, you're gonna rely on Ohm's law and power calculations on literally every single job. You calculate power, that's voltage multiplied by current, to properly match your solar string to your inverter. And just as importantly, you have to calculate voltage drop using current and resistance. Why does that matter? Well, if you size your conductors poorly over a long wire run, you're going to bleed system efficiency and risk dangerous, incredibly costly overheating. Moving right along to Section 2, load analysis and sizing. Before we even look at what the house needs, we evaluate what the sky is giving us using global horizontal irradiance, or GHI. That's what helps us calculate our peak sun hours, which is the true fuel for the entire system. Okay, so the absolutely crucial point here is understanding the difference between two key terms. Sanction load is the hard power limit legally granted by the local utility distribution company, the DISCOM, for a specific meter. Connected load, on the other hand, is the actual real-world usage of the home's appliances. You have to evaluate both. If you design a system based purely on the connected load but totally ignore the sanction limit of the meter, your installation is going to trip limits, fail inspections, and trigger some seriously expensive utility upgrades. No one wants that. When it's time to actually size a system, you're going to follow a few exact steps to break down a client's utility bill. First, calculate the actual AC watt hours the site uses. Then, and this is super important, multiply that by 1.15. That accounts for the energy loss during the inverter's conversion process. Next, divide that by your DC input voltage, which is usually 12 or 24 volts for smaller setups. That correctly translates those AC power demands into the total DC amp hours required. Take that final number, combine it with your site's peak sun hours, and boom, that's your golden ticket to accurately sizing both the battery bank and the PV array. All right, let's bring it all together in Section 3, the physical site survey. Time to step out of the theoretical math and get out into the field. Before you even think about touching a single panel or drilling a single pilot hole, you absolutely must be armed with a very specific toolkit. A clinometer and compass, essential for measuring roof slope and orientation. 3D shading software will map out the sun's path for you. A multimeter validates your electrical potential, and a thermal imager is a total lifesaver for detecting dangerous hotspots. You need every single one of these tools to accurately assess a site's unique physical quirks. Now, I really love this next concept because it completely challenges some long-held assumptions floating around the solar industry. Forget the idea that you should blindly default to pointing panels true south. Just because it's the traditional best practice doesn't mean it's right for your specific project, especially if it completely misses the mark on the client's financial objectives. Here's exactly what I mean. Pointing panels at a 180-degree azimuth, which is true south, is fantastic if your only goal is maximum annual energy yield. But what if your client is on time-of-use utility rates? In that case, you actually want to rotate the array southwest, all the way up to 222 degrees. Why? Because you want to capture peak generation in the late afternoon, right when electricity prices are surging to their absolute highest. You are literally engineering the array to print money when it matters the most. This strategic mindset extends directly to the physical tilt of your panels, too. It's all about manipulating your structural tilt based on geography and grid dependency. For instance, up in northern climates, you'll want to add 15 degrees to your latitude to catch that low winter sun. Down in southern regions, subtract 5 degrees for the best year-round yield. And for off-grid systems where winter power is absolutely mission-critical, you're going to tilt it aggressively, at latitude plus 20 degrees. That sheds snow and captures every last drop of that low-angle winter light. Now, 0.5%. It's a tiny number that seems totally insignificant, right? But it actually represents a massive threat to your system's performance. That is the temperature coefficient. Your solar panels will literally lose 0.5% of efficiency for every single degree they operate above 77 degrees Fahrenheit. Heat is the invisible, silent enemy of solar production. Because heat just absolutely kills efficiency, you might actually want to choose a ground mount over a rooftop if you have the space. Rooftop installations act like giant heat traps, often running 15 to 25 degrees hotter than the ambient air around them. On the flip side, the airflow beneath ground-mounted panels provides natural subpanel cooling. That translates directly into a 2 to 4% baseline performance gain, just by letting the system breathe. But hey, if you do go with a rooftop layout, you've got to execute a flawless structural assessment. You have to verify the integrity of the tile or membrane, you need to assess the live and dead loads, and most importantly, you have to position that array to completely avoid shading from structural elements like chimneys, vents, and dormers. Which brings us right back to our very first warning about the devastating power of a single shadow. During your site survey, you'll use 3D software to simulate seasonal sun paths. If you're building a ground mount, you have to calculate the exact inter-row spacing. If your rows are packed too tight, that front row is going to cast a shadow right onto the rear panels when the sun dips low. You've got to use precise geometry to completely engineer out the risk of microshading. And you always optimize specifically for the winter solstice, when that sun angle is at its absolute lowest point of the year. The best part? You don't just have to trust the software. You can physically prove these shading concepts yourself out in the field. Take a single panel out into the sun, connect your multimeter to the terminals and record the base voltage. Then, just slowly drag a piece of cardboard or even cast your own shadow across the panel's cells from one end to the other. You will literally watch the devastating voltage drop happen in real time right there on your meter screen. It's an incredible, hands-on way to make the invisible forces of solar physics completely visible. So, with these foundational tools in your back pocket, from understanding that atomic-level PV effect to accurately calculating loads based on peak sun hours to engineering the absolute perfect tilt and azimuth, I want to leave you with a thought. Knowing the hidden costs of a single shadow and understanding the massive impact of heat, how are you going to immediately apply these scientific principles and field techniques to optimize your very next project site? Think about it.